So in this video, we're going to look at the imaginary unit I, which continues our conversation of using square roots to solve quadratic equations. So yesterday we looked at equations like x squared equals 9. But what about the equation x squared equals negative 9? Could we come up with solutions to this equation? And well, we really only have two options, right? We could say, what if x equals 3? Well, that's not going to work because 3 squared equals positive 9. What about x equals negative 3? That's also not going to work because negative 3 squared also equals positive 9. So this equation has no real solutions, meaning there's no real numbers that have that solution. So in order to work with square roots of negative numbers, we can't use the real numbers, which is why we turn to the imaginary numbers. So we use the imaginary unit I. Now the number I is defined as the square root of negative 1. This is a new number. When is the last time you learned a new number? That's kind of cool. So this is a new number, like 50 gazillion, like a number you've never heard of before. I is a number, kind of like pi is a number. I is a number, and it stands for the square root of negative 1. Now, here's what's weird. It doesn't really help us find the value of the square root of negative 1, but what it does is it serves as a placeholder so that we can work with the rest of the expression. In many of these cases, these values end up working themselves out of the problem. Here's an example of that. If I have I equal to the square root of negative 1, then what would happen if I did I squared? Well, I squared would be the square root of negative 1 squared. And what happens when we square a square root? They're inverses of each other, so they cancel out. So the square of I squared is negative 1. Now we're back to a real number. And so squaring an I takes you from imaginary numbers to real numbers. So this is where they're kind of powerful. That I helps us kind of hold the imaginary part out to the side while we do some other stuff. And then we hope that eventually we can get back to the real numbers. So we can use the same properties of square roots to simplify. So if I have something like the square root of negative 9, well, I can use my radical properties to break this apart. If I split it up to be the square root of negative 1 times the square root of 9, I know because of what we just talked about that the square root of negative 1 is the number I, and I know that the square root of 9 is 3, so this becomes the number 3i, okay? Now, complex numbers, which we're going to talk about in a lot more detail later, but complex numbers is a whole set of numbers that contains both a real number component and an imaginary component, and they always come in the form a plus bi. So a is a real number piece, and the bi is the imaginary piece. When we solve quadratic equations, a lot of times we're going to obtain complex solutions. So let's go back to what we did with solving square roots and solve these equations. This opens up a lot of possibilities to us now. So number 11, we have 2x squared equals negative 40. So I'm going to solve this just the way we did with square roots. I'm going to divide by 2, and that gives me x squared equals negative 20. Well, now I square root both sides, and before, if we tried to square root a negative, we would have just said, uh-oh, but now we know what to do because of this imaginary number I. So for the square root of negative 20, don't forget our plus or minus, but to simplify this, we're going to have the square root of negative 1, that's the I piece. We're going to have the square root of 4 and the square root of 5. That's the simplifying just like normal. So we have, this is going to be an I, this is going to be a 2. So we're going to write our answer as 2i. Just the same way you wouldn't write x2, we would always write 2x. We treat I kind of like a variable, even though it's not. So I would write 2i root 5. That's how I would write my final answer. Basically, anytime you have a negative under a radical, you're going to have an I at the end. So for example, here's a couple of short examples. If I just have the square root of negative 4, I know that the square root of 4 is 2, but since it's negative, it's going to be 2i. If I have the square root of negative 18, I know that the square root of positive 18 is 9 times 2, so it's 3 root 2. But because it's negative, it's going to be 3i root 2. Anytime you have a negative, you're going to get an I when you simplify it, okay? Now, number 12 is going to be very similar because we are going to subtract 7 and then take the square root of both sides. So we'll start by subtracting 7 from both sides. That gives us x minus 4 squared equals negative 7. Square root both sides. So we get x minus 4 equals plus or minus. Now 7 doesn't have any perfect square factors, but we do have the negative, so that means we need an I in order to make our square root positive. We don't want to leave negatives under the square root, so we bring the I out in front like that, okay? And then just like before, I'm going to add 4 to both sides and put it in front of the plus or minus. So x equals 4 plus or minus I root 7. And that would be how we would write our final answer. Okay? So it doesn't change the process any. Let me give you one more to try simplifying just so you can kind of practice this yourself. See if you can simplify the square root of negative 200. See if you can write that down on your paper. So think about it this way. Since 200 is 100 times 2, and 100 is the perfect square, okay, the square root of 100 is 10, and then we have root 2, but we need the I because of the negative. That's always how it's going to work. To get the negative out, you're going to bring the I to the front. That's always how you fix it. Okay, and even if it's just something simple like the square root of negative 5, that's just going to be I root 5. That's always how we'll handle that, okay? Now, the graph of number 12, if I take the 0 out and put in an f of x and then graph it, the zeros, which is where it's equal to 0, this is what that function looks like. Notice it has no x-intercepts. But it has imaginary solutions. That's an important thing to notice. If an equation has only complex solutions, then the graph of the related function has no x-intercepts. Again, we're always connecting this back to the idea of the functions and what we know. So if I see a graph that doesn't cross the x-axis, I know that if I find the zeros, they're going to be imaginary zeros every single time. Okay? So that is the only extra thing we're adding today, is that your equations might have imaginary solutions. And that is where we're going to stop for today.